What if I told you that everything you learned about gravity in school was not merely incomplete, but fundamentally backwards? That the force you believed pulled you toward the ground, the invisible tether holding planets in their orbits, the cosmic glue binding galaxies together, doesn't actually exist at all. Not in the way you were taught, not in the way Newton imagined, not even close. We begin our story with an apple, the most famous apple in scientific history, falling from a tree in a quiet English orchard, striking the head of a young mathematician and igniting a revolution in human understanding. Isaac Newton's moment of inspiration became the foundation of physics for over 2 centuries. A beautiful, elegant explanation that could predict the motion of cannonballs and planets with astonishing precision. We built empires on Newton's equations. We launched rockets into space using his mathematics. We calculated the orbits of distant worlds with formulas he penned by candlelight 300 years ago. But here is the uncomfortable truth that physics doesn't often reveal in textbooks. Newton was wrong. Not slightly imprecise, not missing a few decimal places, fundamentally, profoundly, beautifully wrong about the very nature of gravity itself. The apple didn't fall because Earth pulled it downward with some invisible force. The moon doesn't orbit our planet because of mysterious attraction acting across empty space. You are not being pulled toward the ground right now as you watch this video. What is actually happening is so strange, so counterintuitive, so magnificently bizarre that when Albert Einstein first proposed the truth, even the greatest minds of his generation struggled to accept it. Gravity, as it turns out, isn't a force at all. It never was. What we experience as gravitational pull is something far more profound, a consequence of the shape of reality itself, a geometry of existence that bends and curves under the presence of mass and energy. We are not being pulled. We are falling through curved spacetime, following the straightest possible paths through a universe that is anything but flat. This revelation, when Einstein unveiled it in 1915, didn't just refine our understanding of gravity. It shattered the entire framework of how we comprehend motion, time, and the fabric of existence itself. And yet, over a century later, most of us still carry Newton's lie in our minds, visualizing gravity as an invisible rope, a phantom force reaching through the void. We teach it to children. We reference it in everyday conversation. We build our intuition around a concept that physics abandoned generations ago. Tonight, we will trace the path from that falling apple to the edges of human comprehension. We will witness the thought experiments that broke reality open. We will examine the evidence that proved Newton's beautiful equations were merely approximations of a far stranger truth. We will explore why this misunderstanding persists and what mysteries gravity still conceals in its curved embrace. Before we drift deeper into this journey through warped space-time and cosmic revelation, I'd love to know, where in the world are you watching from right now? What time is it where you are? Drop a comment below. There's something beautiful about imagining all of us, scattered across the globe, separated by distance and time zones, yet connected in this moment by curiosity and wonder. Now, let us begin. Let us fall together, not toward answers, but toward understanding. Let us discover what gravity truly is and confront the magnificent strangeness of the universe we inhabit. The story starts not with an apple, but with a man brave enough to imagine that everything might be wrong. In 1687, a book was published that would reshape human understanding of the cosmos, Isaac Newton's Philosophia Naturalis Principia Mathematica contained within its pages an equation so elegant, so powerful, that it seemed to unlock the very mechanism of the heavens themselves. With just a few symbols, Newton described gravity as an invisible force pulling objects together, proportional to their masses and inversely proportional to the square of the distance between them. It was revolutionary, it was brilliant, and it was, in a profound sense, a beautiful lie. Newton's equation became the foundation of physics for over 2 centuries. It predicted the motion of planets with stunning accuracy. It explained why apples fall from trees and why the moon orbits Earth. It allowed astronomers to discover Neptune simply by observing irregularities in Uranus's orbit, calculating where an unseen planet must be, and pointing their telescopes to find it waiting exactly where the mathematics predicted. The equation worked so flawlessly that it seemed to reveal the fundamental truth of nature itself. But there was something deeply unsettling hidden beneath this triumph, something that Newton himself could not ignore, could not resolve, and would not pretend to understand. Newton had described how gravity behaved with mathematical precision. He could tell you exactly how strongly the sun pulls on Earth, how fast a cannonball would fall, how the tides rise and fall under the moon's influence. His equations transformed astronomy from mysticism into science, from speculation into prediction. Yet when asked the most fundamental question, the question that lies at the heart of all understanding, Newton had no answer. What is gravity? How does it work? In his own words, written near the end of his life, Newton confessed, "I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses." This was not false modesty. This was an admission from one of history's greatest minds that his masterwork, the equation that bore his name and defined an era of science, was merely a description, not an explanation. He had created a mathematical tool that predicted motion, but he had not uncovered the nature of reality itself. The equation was a map, not the territory, and humanity mistook the map for the landscape. Embedded within Newton's framework was a mystery so profound that it should have haunted every physicist who came after him. Newton's gravity required something impossible: action at a distance. His equation stated that the sun, sitting 93 million miles away across the emptiness of space, pulls on Earth, instantly, continuously, without any physical connection between them. No rope, no chain, no medium, just empty void. Imagine standing on one side of a vast canyon and moving your hand, and instantly, without delay, an object on the far side moves in response. Not because of sound waves traveling through air, not because of light signals, but simply because your hand moved. This is what Newton's gravity demanded. The sun reaches across millions of miles of absolute nothingness and tugs on Earth. Mars feels Jupiter's pull across hundreds of millions of miles. Every object in the universe somehow knows where every other object is and pulls on it accordingly, all without touching, all without any mechanism to transmit this force. How? Newton provided no mechanism. His contemporaries recognized this immediately as deeply troubling. Philosopher and scientist Gottfried Leibniz called it absurd, a return to mysticism wrapped in mathematical clothing. If the sun pulls on Earth through empty space with no intermediary, then we have not explained gravity. We have simply named our ignorance and called it a force. Yet the equation worked. That was the seduction. That was the deception. Newton's predictions were so accurate, so useful, so elegant that the philosophical problem was swept aside. Engineers built bridges using his equations. Astronomers mapped the heavens. The Industrial Revolution was built on Newtonian mechanics. The mathematics became so ingrained in scientific thinking that we stopped questioning what it meant. We stopped asking how gravity worked and contented ourselves with knowing that it worked. Generations of students learned Newton's law as gospel truth. It appeared in textbooks not as a model or an approximation, but as the fundamental nature of reality. Gravity became defined as a force, an invisible pulling between masses, transmitted instantaneously across space. This framework shaped not just physics, but human intuition. We felt that we understood gravity because Newton's equation gave us the power to predict it. But prediction is not understanding. A clock can predict when the sun will rise without comprehending orbital mechanics. A parrot can speak words without grasping their meaning. Newton's equation predicted gravitational effects without revealing what gravity actually is. For over 200 years, the deception held. The equation reigned supreme, unchallenged, seemingly eternal. It became more than science. It became common sense, woven so deeply into our understanding of the universe that to question it felt like questioning reality itself. And then, cracks began to appear. In the mid-19th century, astronomers studying Mercury's orbit noticed something strange. The planet was not behaving exactly as Newton's equations predicted. Mercury orbits closer to the Sun than any other planet, racing around our star every 88 days. But with each orbit, its path shifts slightly. The point of its closest approach to the Sun, called the perihelion, rotates gradually over time. This precession was expected, caused by gravitational tugs from other planets. Newton's equations predicted how much precession there should be, but Mercury's actual precession was faster. Only slightly, just 43 arcseconds per century more than predicted, but that tiny discrepancy was undeniable. An arcsecond is 1/3600th of a degree, so 43 arcseconds is barely more than 1/100th of a degree per century. It seems insignificant, a rounding error, a measurement anomaly. But in science, tiny discrepancies are often the whispers of revolution. Astronomers proposed explanations. Perhaps there was another planet, even closer to the Sun, an undiscovered world called Vulcan, whose gravity tugged on Mercury and explained the extra precession. They searched the skies. They pointed telescopes toward the Sun during eclipses, hoping to spot this hidden planet silhouetted against the solar disk. Vulcan was never found, because it did not exist. Other explanations were offered. Perhaps the Sun was not perfectly spherical. Perhaps there was dust between Mercury and the Sun affecting its orbit. Perhaps Newton's equation needed a slight modification, a small adjustment to account for extreme proximity to massive objects. But none of these explanations worked. Every attempt to save Newton's framework felt forced, artificial, a patch over a crack rather than a solution to the underlying problem. The truth was far more profound and unsettling. Newton's gravity was not wrong, but incomplete. It was a shadow of a deeper reality, an approximation that worked beautifully at human scales, at planetary distances, at everyday speeds, but began to fail when conditions became extreme. Close to the Sun, where gravity is intense and space-time itself begins to curve dramatically, Newton's equations could not capture what was truly happening. Mercury's orbit was not misbehaving. The universe was revealing that our understanding of gravity, the framework we had trusted for centuries, the equations we had built civilization upon, was missing something fundamental. Newton had given humanity a tool of extraordinary power and precision. His equations were not useless. They were not lies in the conventional sense. Even today, we use Newtonian mechanics to launch satellites, navigate spacecraft, and design structures. His work was a monumental achievement, a necessary step in humanity's quest to understand the cosmos. But it was a step, not a destination, a model, not the truth. The deception was not Newton's fault. He never claimed to understand gravity's true nature. The deception was ours, in mistaking a beautiful mathematical description for reality itself, in allowing the success of predictions to silence our deeper questions about mechanisms and meaning. As Mercury traced its stubborn path around the Sun, refusing to conform perfectly to Newton's predictions, the universe was offering a clue. Gravity was not a force pulling across empty space. It was something stranger, something more profound, something that would require a complete reimagining of space, time, and the fabric of reality itself. The Newtonian era was ending. What came next would shatter every intuition we had built about how the universe works. In 1907, a young patent clerk sat at his desk in Bern, Switzerland, surrounded by technical drawings and patent applications. His name was Albert Einstein, and he had recently shaken the foundations of physics with his theory of special relativity. But something troubled him. His elegant equations describing space and time had a glaring limitation. They didn't account for gravity. Newton's laws still reigned supreme in that domain, and Einstein knew with absolute certainty that they were incomplete. Then, in what he would later call the happiest thought of my life, Einstein had a vision. He imagined a man falling from the roof of a building. Not a pleasant image, perhaps, but in that singular moment of creative insight, Einstein saw something no one had seen before. The falling man, plummeting toward the ground, would feel nothing, no downward pull, no sensation of weight. In those terrifying seconds of free fall, the man would be completely weightless, as if gravity itself had vanished. If he released an object from his hand, it would hover beside him, falling at exactly the same rate. To the falling man, gravity would simply cease to exist. This was not merely an observation. It was a revelation that would reshape our understanding of reality itself. Einstein sat upright at his desk, his mind racing through the implications. The sensation we call gravity, he realized, is not actually gravity at all. It is the resistance to gravity. When you stand on the ground, you feel weight, not because gravity is pulling you down, but because the ground is preventing you from falling. Remove that resistance, eliminate that floor beneath your feet, and gravity disappears from your experience entirely. The falling man feels nothing because he is finally moving the way the universe naturally wants him to move. He is not fighting against anything. He is surrendering to the geometry of space itself. This insight illuminates one of the most misunderstood phenomena in modern space exploration. When we watch astronauts floating effortlessly aboard the International Space Station, we instinctively describe them as experiencing zero gravity. This is fundamentally wrong. The astronauts are not beyond gravity's reach. Earth's gravitational pull at the station's altitude is still approximately 90% as strong as it is on the surface. If gravity suddenly vanished, the station would fly off into the void in a straight line, never to return. So why do the astronauts float? Because they are falling, continuously, endlessly. The space station is not sitting still in orbit. It is plummeting toward Earth at thousands of miles per hour. But it's also moving forward so quickly that as it falls, Earth's surface curves away beneath it. The station falls and falls and falls, yet never reaches the ground. The astronauts inside are experiencing precisely what Einstein's imagined man experienced, falling from the roof. Pure, uninterrupted free fall. They feel weightless, not because gravity has disappeared, but because nothing is resisting their fall. They are moving exactly as space itself dictates they should move. This realization led Einstein to formulate what would become the cornerstone of his general theory of relativity, the equivalence principle. Imagine yourself sealed inside a windowless metal box, a chamber with no view of the outside world. Inside this box, you stand firmly on the floor. Your feet press against the surface. If you drop a ball, it falls. If you jump, you come back down. Everything feels perfectly normal, exactly like standing on Earth. Now Einstein asks you a question that seems simple but contains universes of meaning. Are you standing on Earth's surface, or are you in deep space inside a rocket accelerating upward at exactly 9.8 meters per second squared? Think carefully. Feel the floor beneath your feet. Watch the ball fall when you release it. Can you tell the difference? Can any experiment performed inside this sealed chamber distinguish between gravitational pull and acceleration through empty space? The answer, Einstein realized, is no. Not just that we lack the instruments to tell the difference, but that there is no difference. The two situations are not merely similar, they are identical. Fundamentally, completely, absolutely identical. Standing on Earth under gravity's influence is indistinguishable from being accelerated upward through space at 9.8 meters per second squared. Gravity and acceleration are two descriptions of the same phenomenon. This equivalence is so precise, so absolute, that it troubled even Einstein when he first grasped its implications. If gravity and acceleration are truly equivalent, and if acceleration is simply motion through space, then what is gravity? The question seemed to answer itself in a way that defied centuries of understanding. What if gravity isn't a force at all? The idea was radical beyond measure. Newton's invisible force, reaching across the void to pull objects together, had explained the cosmos for 2 centuries. It predicted planetary orbits. It calculated tides. It launched projectiles and guided engineers in building bridges. How could something so successful, so thoroughly verified, be wrong? Yet Einstein pressed forward with his thought. If a person in free fall feels no force, then perhaps no force exists. Perhaps what we call gravity is not the universe pulling objects together, but simply the natural, unforced motion of objects following the contours of space itself. A ball dropped from your hand doesn't fall because Earth pulls it down. It falls because that is the straightest possible path through the curved geometry of space-time near Earth's mass. Here, Einstein arrived at the most mind-bending implication of his equivalence principle, an idea so counterintuitive that even today, more than a century later, it challenges our fundamental perception of reality. You are sitting or standing as you experience these words. You feel solid, stationary, at rest. The floor supports you. Gravity holds you in place. But according to Einstein's insight, this feeling is an illusion of perspective. You are not at rest. You are accelerating. Right now. this very moment. The floor beneath you is not simply sitting still, passively resisting gravity's pull. It is actively accelerating upward into your feet at 9.8 meters per second squared. The ground, the building, the entire surface of Earth is accelerating upward through curved space-time, constantly pushing against you, preventing you from following your natural path through space's geometry. You feel weight not because you are being pulled down, but because you are being pushed up, continuously accelerated away from the path you would naturally take if left unobstructed. This is why astronauts feel weightless, not because gravity has released them, but because finally, at last, nothing is pushing against them. They are free to follow space-time's natural curves. They are experiencing what Einstein called geodesic motion, the straightest possible path through curved space. From their perspective, they are not moving strangely at all. They are finally moving correctly. It is we, standing on Earth's surface, who are constantly accelerated away from our natural trajectory. When Einstein first presented these ideas, they seemed like abstract philosophy, mathematical games with no bearing on physical reality. Gravity, as we experience it, feels utterly real, immediate, and forceful. The notion that it might be an illusion created by curved space seemed absurd. But Einstein was not proposing a metaphor or an approximation. He was describing the literal, physical truth of our universe. His thought experiment with the falling man opened a door that could never be closed. Once you truly grasp the equivalence principle, once you genuinely accept that free fall is not falling at all but natural motion, your perception of reality fundamentally shifts. You begin to see Earth not as a solid platform beneath your feet, but as an accelerating reference frame, constantly pushing you away from the path space wants you to take. The floors we stand on are not passive supports. They are active accelerators, cosmic engines constantly pushing upward through the fabric of reality itself. Every moment of every day, you are pressed against an accelerating surface, prevented from following your natural trajectory through curved space-time. The sensation you interpret as gravity's pull is actually the floor's push, an endless upward acceleration that you experience as weight. Einstein's wild imagination transformed a simple observation about falling into a complete revolution in physics. His happiest thought, that moment of insight in a patent office in Bern, revealed that our most basic assumptions about gravity were wrong. Not slightly wrong, not approximately wrong, but fundamentally, deeply wrong. Gravity is not a force reaching across space to pull objects together. It is the shape of space itself, curved by the presence of mass, guiding objects along paths that appear straight to those who travel them. We do not fall because Earth pulls us. We fall because falling is the straightest path through the curved geometry Earth creates in space-time. And when we stand on solid ground, we are not resting. We are being continuously accelerated away from that straight path, pushed upward through space's contours by the ground beneath our feet. This was Einstein's gift to humanity, not just a new theory of gravity, but a new way of seeing reality itself. What began as an imagined man falling from a roof became the foundation for understanding black holes, the expanding universe, gravitational waves, and the very fabric of space-time. All from one thought experiment, all from asking a simple question: what does a falling person feel? The answer changed everything. To understand what Einstein truly discovered, we must first abandon everything we think we know about the stage upon which reality unfolds. For millennia, Humanity believed that space was a vast, empty void, a three-dimensional container in which objects moved and interacted. Time, meanwhile, was thought to be separate, absolute, flowing uniformly like a river that touches nothing and changes nothing. Newton himself believed in this separation. Space was the theatre, time was the clock, and never did the two meet. Einstein shattered this illusion with a single, profound realization. Space and time are not separate entities. They are woven together into a single, unified fabric, a four-dimensional tapestry that physicists call space-time. This is not merely a poetic metaphor. It is the fundamental structure of reality itself. Every event that has ever occurred, every moment you have experienced, every place you have ever been, exists as a coordinate in this vast, interconnected continuum. You are not moving through space and then separately experiencing time. You are moving through space-time, tracing a path through four dimensions with every breath you take. But Einstein's insight went further still, deeper into the heart of what gravity truly is. Mass and energy, he realized, do not create a gravitational force that reaches across the void to pull on distant objects. Instead, they curve the geometry of space-time itself. Imagine reality as a flexible membrane, smooth and flat, when nothing disturbs it. Now place a massive object, a star, a planet, even your own body, onto this membrane. The fabric bends, warps, deforms around the mass. This curvature is not an effect of gravity. This curvature is gravity. When we say the sun has gravity, what we truly mean is that the sun's immense mass creates a deep well in the fabric of space-time. Earth is not being pulled toward the sun by some invisible tether. Earth is simply following the natural contours of curved space-time, traveling along what is called a geodesic, the shortest path through this warped geometry. From Earth's perspective, it is moving in a straight line, but space-time itself is curved, and so that straight line becomes an orbit, a graceful ellipse that repeats endlessly, not because the sun pulls, but because the geometry of reality itself guides Earth's path. To help visualize this, scientists often use the analogy of a bowling ball placed on a trampoline. The heavy ball creates a depression in the fabric, and if you roll a marble nearby, it will curve toward the ball, spiraling inward along the slope created by the depression. This analogy is both brilliantly helpful and dangerously misleading. It is helpful because it allows us to see how mass creates curvature, and how that curvature influences motion. But it is misleading because it suggests gravity requires a downward direction, that the trampoline is being pulled by some external force beneath it. In reality, space-time curvature exists in all directions simultaneously. There is no up or down in the universe. There is only the geometry of space-time itself, bending in response to mass and energy, creating pathways that objects naturally follow. The trampoline analogy also fails to capture the most astonishing aspect of space-time curvature. Time itself is affected. When mass curves space-time, it does not merely warp the spatial dimensions, it warps time as well. In stronger gravitational fields, where space-time is curved more dramatically, time runs slower. This is not a trick of perception or an illusion created by instruments. This is a measurable, absolute difference in the flow of time itself. If you stand at sea level and I stand on a mountain peak, my watch will tick faster than yours. The difference is minuscule, measured in billionths of a second, but it is real. Your head is literally aging faster than your feet. Every moment of your existence The top of your body experiences time slightly differently than the bottom because it sits in a marginally weaker gravitational field. This effect, known as gravitational time dilation, becomes dramatic near massive objects. On Earth, the difference is negligible, but near a black hole, where space-time is curved to its breaking point, time slows so dramatically that an observer falling toward the event horizon would appear to freeze from the perspective of someone watching from a safe distance. Their clock would slow, their movements would stretch, and eventually they would seem to hang motionless at the boundary of the black hole, suspended in time forever, even as from their own perspective they continue falling inward, experiencing time normally until the moment they cross the horizon and are lost to the universe. This warping of time is not merely a cosmic curiosity. It is a practical reality that affects technology we use every day. GPS satellites orbiting Earth must account for gravitational time dilation, or their navigation signals would drift off course by miles within hours. These satellites sit in weaker gravity than we do on the surface, so their onboard clocks tick faster than ours. If engineers did not continuously correct for this difference, recalibrating the satellite clocks to match Earth's surface time, the entire GPS system would become useless within a single day. Every time you use a map on your phone, every time you navigate to an unfamiliar destination, you are relying on Einstein's understanding of curved space-time. You are using general relativity to find your way home. Consider what this means. Every massive object in the universe, from the smallest grain of sand to the largest galaxy, creates a dent in space-time. These dents overlap, interact, and combine in infinitely complex ways. The sun curves space-time, and Earth moves through that curvature. But Earth also curves space-time, and the moon moves through Earth curvature. You, sitting in your chair or walking down the street, curve space-time ever so slightly. The difference you make is imperceptible, but it is real. Space-time bends around you, and the universe, in some infinitesimal way, adjusts its geometry to accommodate your presence. We are not separate from space-time. We are embedded within it. Every movement we make is a journey through four-dimensional geometry. When you walk forward, you are not just moving through space, you are tracing a path through space-time, a world line that extends from your birth to your death, a unique trajectory that no one else will ever follow. Gravity does not pull you down. Gravity is the curvature of space-time around Earth, and you are simply following the natural path through that curvature, accelerating toward the ground, not because a force compels you, but because the geometry of reality itself guides your motion. This is why falling feels weightless. When you jump from a height or ride a roller coaster over a steep drop, you experience free fall, the sensation of weightlessness. In that moment, you are not fighting gravity. You are surrendering to it completely. You are following a geodesic through curved space-time, moving along the path that requires no force, no effort, no resistance. It is only when the ground interrupts your fall that you feel weight again, because the ground is preventing you from continuing along your natural path. The ground pushes up against you, and that push, that resistance, is what we perceive as weight. Gravity itself is not a force acting upon you. Gravity is the shape of reality, and you are moving through it as effortlessly as light travels through the void. Einstein's vision of space-time is not merely a new way to calculate orbits or predict planetary motion. It is a complete reimagining of what reality is. Space is not a passive stage. time is not an unchanging backdrop. Together, they form a dynamic, flexible structure that responds to the presence of mass and energy, curving and bending in ways that determine the paths of everything from galaxies to photons to the atoms in your body. To understand gravity is to understand that the universe is not made of objects moving through empty space. The universe is made of space-time itself, and we are patterns within it, shapes carved into the fabric of existence, moving along curves we cannot see but can measure, predict, and, in Einstein's case, imagine. This realization forces us to confront profound questions. If space-time is a fabric, what happens when it tears? If time can slow down, can it stop? Can it reverse? If massive objects curve space-time, what happens when space-time curves so much it folds back on itself? These are not idle speculations. They are the doorways to black holes, wormholes, and the very edge of what physics can describe. But before we venture into those mysteries, we must first understand how Einstein's radical vision was tested, challenged, and ultimately proven correct. The story of space-time is not complete until we see the evidence that transformed it from elegant theory into undeniable truth. For more than 2 centuries, Newton's gravity stood unchallenged. It was elegant, it was precise, it predicted the motions of planets with such accuracy that it seemed untouchable. Yet Einstein claimed something radical, that gravity was not a force at all, but the curvature of space-time itself. It was a beautiful idea, poetic even. But science does not bow to beauty alone. It demands proof. It demands evidence so compelling that even the most skeptical minds cannot turn away. The proof came not all at once, but in moments of revelation scattered across decades. Each piece of evidence was a crack in Newton's edifice, a whisper from the universe saying, "Look deeper, look again. Everything you thought you knew is incomplete." The first great test arrived on May 29, 1919. It was not conducted in a laboratory, but written across the sky itself during a total solar eclipse. For years, Einstein's equations had predicted something astonishing: that light itself would bend when passing near massive objects. Not because photons have mass in the traditional sense, but because massive objects curve the fabric of space-time, and light, like everything else, must follow those curves. According to Newton, light should travel in perfectly straight lines through empty space. If gravity affected light at all, the effect would be negligible, imperceptible. But Einstein's equations predicted something different. As starlight passed close to the sun, it should bend, and the amount of bending should be precisely twice what Newton's theory would allow if gravity somehow tugged on light. This was testable. This was measurable. This was the moment when theory would meet reality. British astronomer Arthur Eddington led 2 expeditions to observe the eclipse, one to the island of Principe off the coast of West Africa, and another to Sobral in Brazil. The goal was audacious: photograph stars near the sun during the total eclipse when the moon blocked the sun's blinding light, then compare their positions to where those same stars appeared when the sun was elsewhere in the sky. If Einstein was right, the stars near the sun's edge would appear shifted, their light bent by the sun's gravitational curvature of space-time. The conditions were not ideal. Clouds threatened the observations. Equipment was primitive by modern standards. Yet when the photographs were analysed, the results were unmistakable. The starlight had bent. Not by the amount Newton would have predicted, but by the amount Einstein's equations demanded. The measurements matched Einstein's predictions with stunning precision. The announcement was made at a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6, 1919. The chairman, Nobel Prize winner J.J. Thomson, declared it one of the highest achievements of human thought. Overnight, Einstein became a global celebrity. Newspapers around the world proclaimed that Newton had been overthrown. But it was not an overthrow. It was an evolution. Newton's gravity was not wrong. It was incomplete, a beautiful approximation that worked magnificently in weak gravitational fields, but failed when gravity grew strong and space-time curved dramatically. The eclipse was dramatic, public, undeniable, but there was another mystery that Einstein's theory solved, one that had puzzled astronomers for decades. Mercury, the closest planet to the Sun, does not orbit in a perfect closed ellipse as Newton's laws predicted. Instead, its orbit precesses, meaning the point of closest approach to the Sun slowly rotates over time. Astronomers had measured this precession with exquisite accuracy. 574 arc-seconds per century. Most of this could be explained by the gravitational tugs of other planets, but not all of it. There remained an anomaly, a stubborn 43 arc-seconds per century, that Newton's equations could not account for. Some astronomers proposed the existence of an undiscovered planet, Vulcan, orbiting even closer to the Sun, whose gravity would explain Mercury's behavior. Searches were conducted. None were found. The mystery persisted, a whisper that something fundamental was missing from our understanding. When Einstein completed his general theory of relativity in 1915, he immediately applied it to Mercury's orbit. The equations were complex, dense with mathematical intricacy, but when the calculations were finished, the result was breathtaking. The additional 43 arc-seconds of precession fell naturally, inevitably, from the curvature of space-time near the Sun. No hidden planet was needed, no adjustments, no fudging. The theory simply worked. Einstein later said this was one of the happiest moments of his life, the moment when he knew his theory was not just elegant, but true. Mercury's orbit became proof that space-time curvature was not an abstract concept, but a measurable reality governing the motion of worlds. Yet there was more. If massive objects curve space-time, and if gravity is the manifestation of that curvature, then time itself must flow differently in gravitational fields. Near massive objects, where space-time is deeply curved, time should tick more slowly than in regions far from mass where space-time is flatter. This prediction, called gravitational time dilation, seemed almost mystical. How could gravity affect time? The first crude test came in 1959 with the Pound-Rebka experiment, which measured the frequency shift of gamma rays traveling up and down a tower at Harvard University. The results confirmed that time ran slightly faster at the top of the tower than at the bottom, exactly as Einstein predicted. But the definitive proof came in 1971, when physicists Joseph Haffel and Richard Keating placed atomic clocks on commercial airplanes and flew them around the world, both eastward and westward. When compared to identical clocks that remained on the ground, the flying clocks showed tiny but measurable differences in elapsed time. The differences matched Einstein's predictions with stunning accuracy. Time itself was malleable, shaped by gravity and motion. Today, this effect is not just theoretical curiosity, it is practical necessity. The Global Positioning System, GPS, relies on satellites orbiting Earth at high speeds and at altitudes where gravity is slightly weaker than on the surface. If Einstein's corrections for time dilation were not applied, GPS coordinates would drift by miles within days. Every time you use a navigation app, you are benefiting from Einstein's insight that time flows differently depending on where you are in a gravitational field. But perhaps the most profound evidence came a century after Einstein first proposed it. In 1916, Einstein predicted that violent cosmic events, like colliding black holes or exploding stars, would create ripples in spacetime itself, waves of gravitational distortion propagating outward at the speed of light. These gravitational waves would be incredibly faint by the time they reached Earth, stretching and compressing space by amounts smaller than the width of a proton. For decades, detecting them seemed impossible, yet scientists persisted. They built detectors of astonishing sensitivity, twin facilities called LIGO, the Laser Interferometer Gravitational Wave Observatory, with arms stretching 2.5 miles in perpendicular directions. Lasers bounced back and forth along these arms, measuring distances with such precision that they could detect changes 1,000 times smaller than an atomic nucleus. On September 14, 2015, both LIGO detectors, one in Louisiana and one in Washington state, recorded the same signal within milliseconds of each other. The signal lasted less than a second, a faint chirp rising in frequency and amplitude before fading into silence, but encoded in that chirp was the unmistakable signature of two black holes, each about 30 times the mass of the Sun, spiraling together and merging into one. The event occurred 1.3 billion light-years away, releasing more energy in gravitational waves in a fraction of a second than all the stars in the observable universe emit as light. The detection was announced on February 11, 2016. For the first time, humanity had heard the fabric of space-time itself vibrate. Gravitational waves were real. Space-time was not a static stage, but a dynamic entity that could ripple, stretch, and oscillate. Einstein had been right again. And then there are black holes. These objects are the ultimate vindication of Einstein's vision, places where space-time curves so dramatically that even light cannot escape. Newton's gravity had no room for such extremes, but general relativity predicted them naturally. For decades, they were considered mathematical curiosities, perhaps not real. Yet observations began to accumulate. Stars orbiting invisible companions, jets of matter and energy erupting from the centers of galaxies. And finally, in 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow at the center of the galaxy M87, a dark circle silhouetted against glowing gas. The image matched Einstein's predictions with eerie precision. Black holes are not anomalies. They are proof that space-time can be curved beyond imagination, folded into configurations that Newton's equations could never accommodate. Each piece of evidence, from bent starlight to gravitational waves, tells the same story. Newton gave us a powerful tool, an approximation that works beautifully in our everyday world. But Einstein gave us truth. A truth that is stranger, deeper, and more beautiful than we could have imagined. Gravity is not a force pulling objects together. It is the shape of reality itself, and the universe has confirmed it again and again in ways both subtle and spectacular. We do not abandon Newton. We honor him by recognizing that his insights were a stepping stone to something greater. And we honor Einstein by continuing to test his ideas, pushing them to their limits, searching for the boundaries where even general relativity might give way to something deeper still. For now, the evidence is clear. Space-time is real. It curves. It ripples. It shapes the motion of planets and the flow of time itself. And in proving Einstein right, we have learned that the universe is far more wondrous than we ever dared to believe. We have walked through Einstein's revelation. We have seen the evidence. We have watched starlight bend around the sun and witnessed time slow near massive objects. And yet, if you were to ask yourself right now, at this very moment, what is gravity doing to you? Your first instinct would likely be wrong. You would say gravity is pulling you down. It feels so obviously true, so intuitive, so undeniable. But it is not what is happening. The floor beneath your feet is accelerating upward through curved space-time, pushing against you with constant force. You are not being pulled. You are being held, resisted, stopped from following your natural path through the geometry of the universe. Why then, after everything we have learned, do we still get it wrong? The answer lies not in the cosmos, but within ourselves, in the architecture of our minds, in the limitations of our language, in the education we received, and the world we evolved to understand. The persistence of Newtonian thinking is not a failure of intelligence. It is a consequence of being human. Our brains did not evolve to comprehend curved space-time. They evolved on the African savanna, where survival depended on throwing spears at moving targets, catching falling fruit, and predicting the arc of a stone hurled at prey. For these tasks, Newton's laws work flawlessly. An apple falls. A rock flies. The ground pushes back when we step. These experiences are immediate, visceral, and essential to survival. Evolution shaped our intuition around objects that move through space, not around space itself bending and warping beneath those objects. To our ancestors, the concept of a force pulling things down was not just useful, it was invisible, woven into the fabric of perception itself. We do not feel space-time curving. We feel weight. We feel pressure. We feel the sensation of being held against the earth, and our minds interpret this as being pulled downward. This evolutionary inheritance is powerful. It shapes how we see the world before we even have words to describe it. A child drops a toy and watches it fall. They do not think about geodesics or space-time curvature. They think the toy went down because something made it go down. This intuition is hardwired, refined across millions of years, and extraordinarily difficult to overwrite. And then we enter the classroom. Educational systems worldwide, from elementary schools to universities, teach gravity as a force first. Children learn that gravity pulls objects toward the earth. They memorize equations that describe this pull. They calculate the force between masses using Newton's law of universal gravitation. They solve problems, pass exams, and move forward, all while cementing a framework in their minds that is, at its core, incomplete. This is not a mistake. Newton's framework is useful, elegant, and accurate for nearly every practical application. Engineers design bridges using Newtonian mechanics. Aerospace scientists launch rockets using Newton's equations. Even missions to distant planets, like the journey to Jupiter we explored earlier, rely primarily on Newtonian calculations. For these purposes, Einstein's corrections are so small they can often be ignored. But there is a cost to this approach. By teaching Newton first and Einstein later, if at all, we create a foundation built on a beautiful approximation rather than the deeper truth. And once that foundation is set, it becomes the lens through which we interpret everything that follows. Even when students eventually encounter general relativity, they often struggle to fully let go of the force-based model. It lingers in their intuitions, quietly shaping how they think about gravity long after they have learned the mathematics of curved spacetime. The problem is compounded by language itself. We say gravity pulls because we lack intuitive vocabulary for what is actually happening. There is no simple, everyday word for following a geodesic through curved spacetime. There is no phrase that captures the sensation of the ground accelerating upward beneath us. Our language evolved alongside our intuitions, and it reflects the same Newtonian bias. When we describe an apple falling from a tree, we instinctively say it is pulled down by gravity. To describe it accurately, we would need to say the apple is following the straightest possible path through spacetime, and the Earth's surface is accelerating upward to intercept it. This is cumbersome. It is unintuitive. It does not fit the rhythm of natural speech. And so we default to the simpler, incorrect description, reinforcing the misconception with every sentence. This language trap is not limited to casual conversation. Even physicists, when speaking informally, often revert to Newtonian phrasing. They talk about gravitational forces, about objects being pulled, about attraction between masses. They do this not because they misunderstand the theory, but because the alternative is exhausting. Describing every interaction in terms of space-time curvature requires constant mental translation, and our minds naturally seek the path of least resistance. For physics students, this creates a peculiar tension. They learn the mathematics of general relativity. They solve problems involving tensors and metrics. They can calculate how space-time curves around a massive object. And yet, when asked to explain gravity quickly, intuitively, without equations, many will revert to the image of a force pulling things together. The Newtonian intuition persists beneath the surface, waiting to re-emerge whenever the conscious effort to think in terms of curved space-time falters. This is not a flaw in their education. It is a reflection of how deeply our intuitions are rooted. Changing them requires not just learning new information, but actively unlearning old patterns of thought. It requires training the mind to see the world differently, to feel the ground pushing rather than gravity pulling, to recognize that stillness itself is an illusion. And here we arrive at the deeper issue, the philosophical problem that makes Newtonian thinking so persistent. Accepting Einstein's view of gravity means accepting that your perception of reality is fundamentally wrong. It means acknowledging that when you sit in a chair, feeling perfectly still, you are not still at all. You are accelerating. The chair is pushing you upward with constant force, preventing you from following your natural path through space-time. The sensation of weight you feel is not gravity pulling you down. It is the resistance of matter stopping your motion. This realization is disorienting. It breaks the basic assumptions we hold about stillness, about motion, about what it means to be at rest. Our entire experience of the world is built on the idea that the ground is stable, that we stand upon it, that gravity is something external acting upon us. To accept that the ground is accelerating upward, that we are constantly being pushed, requires us to question the very foundation of how we perceive existence. Most people, when confronted with this, do not reject it intellectually. They accept it as true in the abstract, in the realm of physics and mathematics, but emotionally, experientially, they do not internalize it. The old intuition remains intact. They continue to feel gravity as a pull, because that is what their senses tell them. and our minds trust our senses above all else. This is why Newtonian thinking persists. Not because it is correct, but because it is comfortable. It aligns with our experience. It fits our language. It requires no existential adjustment. Newton gave us a model that matches our intuitions so perfectly that even when we know it is wrong, we struggle to let it go. And yet, there is a strange beauty in this persistence. Newton's laws remain useful precisely because they approximate reality so well within the conditions of our everyday lives. For the vast majority of human experience, treating gravity as a force introduces negligible error. The engineers who build skyscrapers, the pilots who navigate aircraft, the athletes who calculate trajectories, all operate successfully within the Newtonian framework. Einstein's truth becomes essential only at the extremes, near black holes, where space-time curves violently, around neutron stars, where gravity warps time itself, in GPS satellites, where relativistic corrections are necessary for accurate positioning. In these realms, Newton fails, and Einstein prevails. But for the rest of us, standing on the surface of Earth, going about our lives, Newton's approximation is close enough. The ground feels solid. Objects fall when dropped. The illusion is so convincing that it becomes indistinguishable from truth. Perhaps then, the persistence of Newtonian thinking is not entirely a problem. It is a reminder that humans navigate the universe not through perfect understanding, but through useful models. We simplify, we approximate, we build frameworks that are good enough to survive, to thrive, to send spacecraft across the solar system. But every so often, we must pause. We must look deeper. We must ask ourselves whether the models we use reflect reality or merely mirror our limitations. And when we do, we find that gravity, the force we thought we understood, is stranger and more profound than we ever imagined. The ground beneath us is not still. It never was. Einstein gave us a new vision of gravity, one that transformed falling apples into curved space-time and bent light around stars. His equations have guided spacecraft, predicted black holes, and revealed the expansion of the universe itself. Yet for all its elegance and power, general relativity is not the final word. It cannot be. Because at the edges of our understanding, where the very small meets the infinitely dense, where quantum mechanics collides with cosmic curvature, Einstein's masterpiece breaks down. Gravity, the force we thought we had finally understood, remains draped in profound mystery. The truth is humbling. We have conquered Newton's limitations only to discover deeper enigmas waiting in the shadows. Questions that challenge not just our equations, but our conception of reality itself. As we peer into the depths of black holes, observe the strange behavior of galaxies, and measure the accelerating expansion of space, we are forced to confront an uncomfortable fact. We still don't truly understand gravity. At the heart of modern physics lies a fundamental crisis, a schism so profound that it has consumed the careers of thousands of brilliant minds. General relativity, Einstein's theory of gravity as curved spacetime, describes the cosmos beautifully at large scales. Planets orbit stars. Light bends around massive objects. Black holes warp time itself. The mathematics is precise, the predictions confirmed, again and again. But when we descend into the quantum realm, the subatomic world where particles flicker in and out of existence and uncertainty reigns supreme, general relativity fails. It simply stops working. Quantum mechanics, the physics of the infinitesimally small, operates by entirely different rules. In the quantum world, particles exist in multiple states simultaneously until observed. Energy comes in discrete packets. Space and time themselves become grainy and uncertain at the smallest scales. This theory has given us transistors, lasers, and computers. It describes 3 of the 4 fundamental forces of nature with stunning accuracy: electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces has been successfully quantized, understood as exchanges of force-carrying particles called bosons. But gravity resists. When physicists attempt to apply quantum mechanics to Einstein's curved spacetime, the mathematics explodes into infinities and contradictions. The equations produce nonsensical answers, predictions of infinite energy and impossible probabilities. At the intersection of the very massive and the very small, where both theories should apply simultaneously, neither works. This is the quantum gravity problem, and it represents the deepest unsolved mystery in theoretical physics. Consider what happens at the center of a black hole. As matter collapses under its own gravity, general relativity predicts that it will continue compressing until it reaches infinite density in a point of zero volume, what physicists call a singularity. Here, space-time curvature becomes infinite. Time itself ceases to flow in any meaningful way. But can infinity truly exist in nature? At such extreme conditions, quantum effects should become dominant, but we have no theory to describe what actually occurs. General relativity breaks down completely. Quantum mechanics has no framework for such warped space-time. We are left staring into a mathematical abyss, unable to answer the most basic question: what is actually there? This isn't merely an academic curiosity. Understanding quantum gravity is essential to comprehending the birth of the universe itself. In the first fraction of a second after the Big Bang, the entire cosmos was smaller than an atom, yet contained all the mass and energy that would become every galaxy, star, and planet. At that moment, quantum effects and gravitational effects were equally important. Without a theory of quantum gravity, we cannot truly understand how the universe began. We cannot peer behind the curtain of the Big Bang to ask whether our universe emerged from something else, or if time itself was born in that moment. Beyond black hole singularities and cosmic origins, gravity presents another profound mystery, one written across the visible universe in patterns we can observe but cannot explain. When astronomers measure the rotation of galaxies, they find something impossible. Stars at the outer edges orbit far too quickly. According to the visible matter, the galaxies should tear themselves apart, yet they remain intact, spinning faster than gravity should allow. The only explanation that fits is invisible mass, vast amounts of it, holding galaxies together with gravitational force we can measure but cannot see. We call it dark matter, though the name is more confession than description. We don't know what it is. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any way we can detect. It makes up approximately 85% of all matter in the universe, outnumbering ordinary atoms by more than 5 to 1, yet we have never directly detected a single particle of it. Dark matter reveals itself only through gravity. We see its effects in the rotation curves of galaxies, in the gravitational lensing of distant light, in the cosmic web of structure stretching across billions of light years. Gravity tells us it's there, yet every other sense we possess finds nothing. Is it a new type of particle? a modification of gravity itself at galactic scales? Could Einstein's equations be incomplete in ways we haven't imagined? Decades of sensitive experiments searching for dark matter particles have found nothing. The mystery deepens with every null result. If dark matter confounds us, dark energy terrifies the very foundations of cosmology. In the late 1990s, astronomers measuring distant supernovae made a discovery that defied all expectations. The universe's expansion is not slowing down, as gravity should demand. It is accelerating. Galaxies are flying apart from each other at an increasing rate, as if some invisible force is pushing against gravity's curvature of space-time itself. This acceleration requires energy, enormous amounts of it, permeating every cubic meter of space. We call it dark energy, and it comprises roughly 68% of the total energy content of the universe. Yet we have no idea what it is. Is it a property of space itself? An intrinsic energy of the vacuum? Is it a new field permeating the cosmos? Or is it evidence that general relativity fails at the largest cosmological scales? Dark energy's existence forces us to confront unsettling possibilities. If the acceleration continues, the universe will expand forever. Galaxies will recede beyond our ability to see them. And in trillions of years, intelligent beings will look up at a sky containing only their local galaxy, unaware that anything else exists. The observable universe will contract to a single island of light surrounded by darkness. Our descendants, if any survive, will live in a cosmos fundamentally different from our own. Together, dark matter and dark energy constitute 95% of the universe. Everything we can see, measure, and understand, all the atoms that make stars, planets, and ourselves, represents a mere 5% of cosmic reality. Gravity reveals the presence of this hidden 95%, yet tells us nothing about its nature. We are like ancient cartographers who can trace the outline of continents, but cannot explain what lies within. Even within the 5% we think we understand, gravity presents puzzles that mock our confidence. Of the four fundamental forces of nature, gravity is by far the weakest, vastly, incomprehensibly weaker. A small refrigerator magnet can overcome the gravitational pull of the entire Earth. The electromagnetic force between two protons is 10⁻36 times stronger than their gravitational attraction. That's a trillion times more powerful. Why? Why is gravity so feeble compared to the other forces? This hierarchy problem has no answer within our current theories. Some physicists suggest that gravity only appears weak because it is diluted, leaking into dimensions we cannot perceive. While electromagnetism and the nuclear forces are confined to our familiar 3 dimensions of space, gravity might propagate through additional hidden dimensions, spreading its influence across a higher dimensional space and appearing weak in our limited slice of reality. String theory, one of the leading candidates for a theory of quantum gravity, requires the existence of 6 or 7 extra spatial dimensions beyond the 3 we experience. These dimensions must be compactified, curled up so small that we cannot detect them, but gravity might access them. If true, at very small distances or very high energies, gravity could suddenly become as strong as the other forces. Large particle colliders search for evidence of these extra dimensions, looking for signs that gravity behaves differently at high energies. So far, they have found nothing. The dimensions, if they exist, remain hidden. The search for quantum gravity has another goal beyond mathematical elegance. If gravity is truly a fundamental force like the others, it should be mediated by a particle, a graviton, the quantum of gravitational waves. Just as photons carry the electromagnetic force and gluons carry the strong nuclear force, gravitons should carry gravity. Einstein's theory, viewed through quantum eyes, predicts their existence. But we have never detected one. Gravitons, if they exist, interact so weakly with matter that catching one might be impossible with any technology we can imagine. When LIGO detected gravitational waves, ripples in space-time itself, it measured the collective behavior of countless gravitons, like hearing the ocean without distinguishing individual water molecules. The waves confirmed that space-time can oscillate and propagate disturbances, but the quantum nature of gravity remains invisible. This measurement problem cuts to the core of physics. Can something exist if it is fundamentally undetectable? Is the graviton a real particle we simply cannot measure, or is it a mathematical artifact, a convenience of our theories that has no physical reality? The question echoes through laboratories and equations unanswered. These mysteries are not failures of science but invitations. They mark the boundaries where our understanding ends and true exploration begins. Every answered question has revealed deeper questions beneath. Newton gave us an equation. Einstein gave us curved space-time. Now we search for something more profound, a theory that unites the quantum and the cosmic, that explains dark matter and dark energy, that reveals why gravity is weak and whether reality contains hidden dimensions beyond our perception. Somewhere in the mathematics, in observations yet to be made, in experiments yet to be conceived, lies the next revolution in our understanding of gravity. It will not make Einstein wrong, just as Einstein did not make Newton wrong. It will reveal that both were glimpses of something larger, facets of a deeper truth we are only beginning to perceive. The universe keeps its secrets well. But gravity, the force we thought we understood, continues to whisper hints of mysteries waiting just beyond the edge of comprehension. Right now, at this very moment, as you watch these words appear on your screen, you believe you are sitting still. You feel stationary, grounded, at rest. But you are not. You are accelerating, not through space in the conventional sense, but through space-time itself, racing upward at 9.8 meters per second squared. This is not metaphor. This is not poetry. This is the literal truth of living in curved space-time. And once you understand it, your perception of reality will never be the same. The ground beneath you is not passive. It is pushing up against you with constant, relentless force. What you have always called the sensation of weight, what you have felt every moment of your existence, is not gravity pulling you down. It is the Earth's surface pushing you up, preventing you from following your natural path through curved space-time. You are like a person pressed against the wall of an accelerating elevator, feeling the force not because something pulls you backward, but because the elevator pushes you forward. The difference is that your elevator is the surface of the Earth, and it never stops accelerating upward through the geometry of space-time itself. This revelation transforms everything. When you stand, you are being pushed. When you sit, you are being pressed. When you lie down to sleep, you are being held against the fabric of reality by a planet that curves space-time so profoundly that your natural trajectory bends toward its center. In the absence of the ground, you would not fall down. You would simply follow the straightest possible path through curved space, a path that happens to lead toward the Earth's core. No force would act upon you. You would be in free fall, and in free fall, you would experience no gravity at all. Astronauts aboard the International Space Station are not floating because there is no gravity. They are floating because they are falling continuously, endlessly around the Earth. They follow the curved paths that space-time dictates, and in doing so, they experience weightlessness. They are not escaping gravity. They are embracing it completely, surrendering to the geometry of the universe without resistance. This is what it means to move freely through space-time. No push, no pull, only the elegant curve of reality itself. But the implications go far deeper, stranger, more profound than the mere sensation of weight. Living in curved space-time means that time itself becomes malleable, variable, dependent on where you are and how fast you move. This is not science fiction. This is not speculation. This is measured, proven, undeniable reality. Time travel to the future is real, and it happens every day. Astronauts who spend months aboard the International Space Station return to Earth, having aged slightly less than those who remained on the ground. The difference is minuscule, measured in milliseconds, but it is real. Space-time curves less intensely at the altitude of the station than it does on Earth's surface. Time flows faster where gravity is weaker. The astronauts have traveled into the future, if only by the smallest fraction. They have experienced time dilation, the stretching and compressing of moments depending on the curvature of space-time around them. GPS satellites must account for this effect constantly. They orbit at altitudes where space-time is less curved than on the ground, so their onboard clocks tick faster than clocks on Earth's surface. If engineers did not correct for this time dilation, GPS navigation would fail within minutes, accumulating errors that would render the system useless. Every time you use GPS to navigate, you are relying on the reality of curved spacetime. You are trusting that time flows differently depending on where you are in a gravitational field. The precision required is astonishing. A difference of mere microseconds per day would cause navigational errors of miles. Now imagine standing near a black hole at the edge of the most extreme curvature space-time can achieve without collapsing entirely. Here, time dilation becomes not a subtle effect measured in microseconds, but a profound distortion that reshapes the experience of existence itself. If you could survive near the event horizon of a supermassive black hole, hovering just beyond the point of no return, you would witness something incomprehensible. Time for you would slow to a crawl compared to the rest of the universe. Seconds for you would be years, decades, centuries for those far away. If you watch the distant stars, you would see them move across the sky in accelerated motion, like a time-lapse film of the cosmos. Civilizations would rise and fall in what felt like moments. Galaxies would spiral and collide in the blink of an eye. You could watch the entire future of the universe unfold before you, while experiencing only a brief passage of time yourself. This is not theoretical fantasy. This is what general relativity predicts, and every test we have ever conducted confirms its accuracy. Near a black hole, you become a time traveler, not by moving faster than light, but by standing still in the most curved region of space-time the universe allows. The future comes to you, rushing past while you remain suspended in a stretched moment, witnessing epochs compressed into instants. But you do not need a black hole to experience the strangeness of living in curved space-time. The effects are here, now, subtle but real, woven into the fabric of your everyday existence. Consider this. Your body is longer when you lie down than when you stand up. Not because your spine decompresses, though it does. Not because your muscles relax, though they do. But because time flows at different rates between your head and your feet. When you stand, your feet are closer to the Earth's center of mass than your head. They experience slightly stronger gravitational time dilation. Time moves infinitesimally slower at your feet than at your head. This difference is unimaginably small, but it is real, and it means that the spacing of events, the flow of processes, the ticking of molecular clocks within your cells, all occur at subtly different rates along the length of your body. You are not a single moment moving through time. You are a gradient of moments, each part of you experiencing time at a slightly different rate. When you lie down horizontally, the difference between your head and feet diminishes. The gradient flattens. In a sense, you become more unified in time, more coherent as a single entity moving through space-time together. This might sound absurd, impossible to perceive, irrelevant to daily life, and yet, the most precise atomic clocks in the world can measure the difference in time dilation between heights, separated by mere centimeters. Raise a clock by a single foot, and it will tick faster than an identical clock on the floor below. The universe keeps different time depending on where you stand. You live in a reality where up and down are not just directions in space, but directions in time itself. Every structure, every building, every mountain experiences this. The top of the Eiffel Tower ages faster than its base. The summit of Mount Everest has experienced more time than its foothills. The difference is immeasurably small by human standards, but over geological timescales, over cosmic epochs, these differences accumulate. The universe is not a single ticking clock. It is an infinite symphony of clocks, each keeping its own rhythm dictated by the curvature of space-time around it. Perhaps the most profound implication of living in curved space-time is this: nothing falls because a force pulls it down. Objects fall because space-time itself is curved, and they are simply following the straightest possible path through that curvature. The Earth does not exert a force on the Moon to keep it in orbit. The Earth curves space-time, and the Moon moves through that curvature in a path that happens to loop endlessly around our planet. No strings, no invisible hands, no force reaching across the void, only geometry, only the shape of reality responding to the presence of mass. You are not being pulled toward the Earth's center. You are trying to move through time, as all things must, and the presence of Earth's mass has curved the fabric of space-time so dramatically that moving forward through time naturally carries you toward the planet's core. The ground interrupts that path, pushing you away from your natural trajectory, and you feel that interruption as weight, as gravity, as the force holding you down. But it is not gravity that holds you. It is the ground that pushes you up, away from the path you would naturally follow through the curved architecture of the universe. This is what it means to live in curved space-time. Every moment, every sensation, every experience is shaped by the geometry of reality itself. You are not separate from space-time. You are woven into it, inseparable from its contours and curves. Your existence is not a sequence of moments in static space, but a trajectory through a dynamic, shifting fabric that bends and warps in the presence of mass and energy. You are not a traveler through the universe. You are the universe experiencing itself, moving along paths carved into the structure of reality by the presence of matter and the passage of time. To live is to curve space-time simply by existing. To move is to navigate the geometry your own mass helps create. In this sense, we are all sculptors of reality, shaping the fabric of the cosmos with every breath, every heartbeat, every step forward through the infinite curvature of existence itself. We stand at the threshold of a new era, where gravity is no longer just something we measure, but something we may one day control. The future beckons with theories so strange, they seem like science fiction, and technologies so profound, they could reshape civilization itself. Einstein's general relativity, elegant as it is, remains incomplete. It describes gravity beautifully at the scale of planets and stars, but when we descend into the quantum realm, into the universe of atoms and subatomic particles, the equations begin to break down. Here, where distances become impossibly small and energies incomprehensibly high, gravity stops making sense. The smooth fabric of space-time that Einstein described becomes fractured, pixelated, refusing to cooperate with the rules that govern the quantum world. This is the great, unsolved mystery of modern physics. How do we unite gravity with quantum mechanics? Two of the most successful theories ever conceived, yet they speak different languages, describe different realities. At the heart of a black hole, where quantum effects and extreme gravity collide, both theories fail simultaneously. The universe simply says, "Not yet, you do not understand me completely." Enter string theory, one of the most ambitious attempts to reconcile this cosmic paradox. In string theory, particles are not point-like dots, but tiny vibrating strings of energy, each resonating at different frequencies like cosmic violin strings. Different vibrations produce different particles, electrons, photons, quarks. And among these vibrations, one particular frequency produces the graviton, the theoretical quantum particle of gravity itself. In this framework, gravity emerges naturally from the quantum realm. It is not separate from quantum mechanics, but a manifestation of it, woven into the very fabric of how strings vibrate through higher dimensions we cannot directly perceive. String theory suggests that space-time itself has more dimensions than we experience. While we live in 3 spatial dimensions plus time, the mathematics demands 10 or 11 dimensions total. The extra dimensions are hidden, curled up so small that we cannot detect them, yet they shape the fundamental forces we observe every day. Gravity, in this view, may feel weaker than other forces, not because it truly is weaker, but because it leaks into these hidden dimensions, diluting its strength across spaces we cannot see. To test string theory is to probe distances smaller than anything we can currently measure, energies higher than any particle accelerator can reach. We stand before a theory of such mathematical beauty that it demands to be true, yet remains tantalizingly beyond our experimental grasp. But string theory is not the only contender. Loop quantum gravity takes a radically different approach. Instead of tiny strings, it proposes that space-time itself is not smooth and continuous, but granular, made of discrete quantum loops woven together like an invisible mesh. At the smallest scales, the Planck scale, about 10 to the negative 35 meters, space-time becomes pixelated. Space and time themselves come in minimum units, indivisible chunks that cannot be subdivided further. In this view, when you zoom in far enough, the fabric of reality looks less like Einstein's smooth rubber sheet and more like a cosmic chainmail, each link a quantum loop vibrating with geometric information. Loop quantum gravity offers tantalizing solutions to problems that plague other theories. Inside a black hole, where general relativity predicts a singularity, a point of infinite density, where physics breaks down completely, loop quantum gravity suggests something different. The quantum loops prevent true singularities from forming. Instead of infinite collapse, matter reaches a maximum density and then, perhaps, bounces back, creating a bridge to another region of space-time or even another universe entirely. The Big Bang itself in this framework may not be a true beginning, but a bounce, a cosmic rebound from a previous contracting universe. Time extends backward beyond what we thought was the origin of everything. These theories remain unproven, existing in the realm of mathematics and speculation. But the future promises ways to test them, and that future has already begun. September 14, 2015 marked a turning point in human history, though most of the world did not immediately realize it. On that day, two laser interferometers separated by thousands of miles both detected a ripple in space-time itself, a gravitational wave produced by two black holes colliding over 1 billion light-years away. For the first time, humanity heard gravity speak, not through light, not through particles, but through the fabric of space-time vibrating like a cosmic bell. Gravitational wave astronomy is not just a new tool, it is an entirely new sense, like suddenly gaining the ability to hear after a lifetime of silence. For all of human history, we have observed the universe through electromagnetic radiation, light, radio waves, X-rays, each revealing different aspects of cosmic phenomena. But gravitational waves carry information that light cannot. They pass through matter virtually undisturbed, traveling across the universe from events so violent they warp the very geometry of existence. Colliding black holes, merging neutron stars, possibly even echoes from the Big Bang itself, all leave their signature in the ripples of space-time. As detectors become more sensitive, as new observatories come online in space and on Earth, we will map the universe not by what we see, but by how space-time itself trembles. We will witness events invisible to any telescope, peer into the hearts of neutron stars, where matter becomes so dense that a teaspoon would weigh as much as a mountain, observe the final moments of black holes as they spiral together and merge in catastrophic union. Gravitational waves will reveal a hidden universe, one that has been singing all along, waiting for us to develop ears to hear it. But the future of gravity extends beyond observation. It reaches toward manipulation, toward control. The effects of gravitational time dilation, once merely a curiosity to test Einstein's predictions, are now being harnessed for practical technology. Atomic clocks so precise they can detect the time difference caused by elevating them just a few centimeters above the ground are enabling new forms of GPS navigation, quantum computing, and fundamental physics experiments. These clocks experience time differently based on their position in Earth's gravitational field, and by measuring these infinitesimal differences, we can map space-time curvature with unprecedented precision. Imagine a future where we use gravitational time dilation not as an obstacle, but as a resource. Quantum computers utilizing the slight time differences at different gravitational potentials to perform calculations in parallel across subtly different time streams. Ultra-precise sensors that detect underground structures, hidden caves, or mineral deposits by measuring minute variations in local space-time curvature. The technology to map not just the surface of the Earth, but the fabric of space-time itself, revealing invisible architecture beneath our feet and throughout the solar system. Yet the deepest question remains unspoken but tantalizing. Could we ever manipulate space-time curvature directly? Could we create or cancel gravitational fields at will? True anti-gravity technology seems to violate everything we understand about physics. Gravity is not a force you can simply reverse or shield against. It is the curvature of space-time produced by energy and mass. To create anti-gravity would require exotic matter with negative mass or negative energy density, substances that, as far as we know, do not exist in nature. And yet the universe has surprised us before. Dark energy, the mysterious force accelerating the universe's expansion, effectively acts as anti-gravity on cosmic scales. If we could understand dark energy, harness it, concentrate it, perhaps space-time manipulation is not impossible, merely unimaginably difficult. Perhaps future civilizations will look back at our era the way we look back at a time before electricity, marveling that we could observe space-time curvature but not shape it, measure gravitational waves but not generate them at will. What studying gravity teaches us extends far beyond physics and engineering. It reveals something profound about the nature of reality itself. We live our entire lives experiencing what we think is a force pulling us downward, when in truth, we are simply following the straightest possible path through curved space-time. Our most fundamental, constant, universal experience of reality, the feeling of weight, the pull toward the earth, is something we completely misunderstood for millennia. This is both humbling and exhilarating. If we were so profoundly wrong about gravity, something we experience every waking moment of our existence, what else might we be misunderstanding? What other aspects of reality are we interpreting through the lens of intuition rather than truth? Time, consciousness, causality itself. All may be radically different from what they appear to be. The future of gravity is not just about new theories and technologies. It is about continuing the journey of questioning our most basic assumptions about existence. It is about recognizing that the universe is under no obligation to make sense to us, to conform to our intuitions, to be comprehensible at first glance. And yet, through observation, experimentation, and imagination, we can come to understand it, not as we wish it to be, but as it truly is. The story of gravity, from Newton's falling apple to Einstein's curved space-time, to gravitational waves rippling across the cosmos, is the story of humanity learning to see beyond appearances, to question comfortable certainties, to embrace beautiful and unsettling truths. And that story is far from over. The next chapter is being written now, in laboratories and observatories around the world, by physicists and dreamers asking questions whose answers we cannot yet imagine. The future of gravity is the future of understanding reality itself, and that future has never been more extraordinary. We have journeyed through centuries of human understanding, from Newton's elegant mathematics to Einstein's revolutionary vision. Now, as we stand at the edge of this exploration, we must ask ourselves, what have we truly discovered? The answer is both simple and profound. Gravity is not a force pulling you down. It never was. You are accelerating upward through the curved geometry of space-time itself. The ground beneath your feet is pushing you, constantly accelerating you through the fabric of reality, while space-time bends around the mass of Earth. This is not metaphor. This is the beautiful truth we completely misunderstood. The shift in perspective is staggering. For centuries, We imagined gravity as an invisible hand reaching across empty space, mysteriously pulling objects together. We treated it as one of nature's fundamental forces, something that required explanation but could never truly be understood. Einstein showed us otherwise. Gravity is not a force at all. It is geometry. It is the shape of space-time itself, curved by mass and energy, creating pathways that objects follow, not because they are pulled, but because straight lines in curved space look like orbits, falls, and trajectories to our limited perception. This revelation transforms everything. The apple falling from Newton's tree is not being pulled downward. It is following the straightest possible path through space-time that has been warped by Earth's presence. The moon orbiting Earth is not held by invisible strings. It is traveling in a straight line through curved four-dimensional geometry. You, standing still right now, are not motionless. You are accelerating upward at 9.8 meters per second squared, held in place by the electromagnetic forces in the ground pushing against you. Time itself flows at different rates depending on how deep you sit in gravity's geometric well. Yet here is the remarkable truth. Getting this wrong for so long is not a failure of human intelligence. It is a testament to our persistence, our curiosity, our refusal to accept mysteries without seeking deeper understanding. Newton's equations still work brilliantly for most everyday purposes. They send humans to the moon, guide satellites through orbit, and predict planetary motion with stunning accuracy. Newton was not wrong. He was incomplete, and Einstein's general relativity, magnificent as it is, may itself be incomplete, a stepping stone to an even deeper understanding we have yet to discover. This is the beauty of science. We do not arrive at ultimate truth and stop. We refine, we question, we push deeper into the unknown. Each generation builds upon the insights of those who came before, not by discarding their work, but by expanding it, seeing further because we stand on the shoulders of giants. So I ask you now, what other fundamental truths about reality might we be completely misunderstanding? If gravity, one of the most familiar forces, one of the most familiar experiences of existence, turns out to be something entirely different than we believed, what else are we missing? Time, consciousness, the nature of matter itself. The questions stretch endlessly into the future, waiting for curious minds to explore them. Before you go, leave a comment below and tell me where in the world, or perhaps where in curved space-time, you're watching from. If this journey through gravity's true nature expanded your mind, hit that like button and subscribe for more explorations into the mysteries that define our universe. Remember, the ground beneath you is not still. You are accelerating upward through the cosmos, riding the curvature of space-time itself. That is not a force, that is reality. And reality, when truly understood, is far stranger and more beautiful than we ever imagined.